For over 50 years, Christopher Dunn has been measuring things for a living. Not with a tape measure and a pencil, with precision instruments calibrated to 5/100,000ths of an inch. The kind of tools used to manufacture components for jet engines, satellite guidance systems, and surgical implants. Tools where a deviation the width of a human hair means the part gets scrapped and the production line shuts down. He is not an archaeologist. He is not a historian. He is not a television personality with a theory to sell. He is a manufacturing engineer who has spent his entire career in aerospace, building parts where precision is the difference between flight and catastrophe. And in 1986, on what was supposed to be a tourist trip, he walked into the Great Pyramid of Giza, placed his hands on the granite walls of the king's chamber, and saw something that stopped him cold. Not the scale, not the age, not the hieroglyphs, the marks. Strange, precise, repeating marks cut into the hardest stone known to the ancient world. Saw cuts that ran straight and true across surfaces measured in feet. Drill holes with walls so smooth and circular they could have been bored yesterday. Surfaces polished to a mirror finish across granite that rates 7 on the Mohs hardness scale, harder than steel, harder than iron, harder than anything in an ancient Egyptian toolkit. Marks that, to his trained eye, did not come from copper chisels and stone hammers. Marks that looked exactly like the ones left by industrial machinery in his own factory back in the American Midwest. The same spiral grooves, the same flat surfaces, the same sharp internal corners that only emerge when a guided, controlled cutting process meets hard material with sufficient force and rigidity. He did not say this publicly at first. He went home, read everything Egyptologists had written about ancient stoneworking methods, and waited for the explanation that would make the marks make sense. It never came. So he went back and back again. 9 trips in total, over 4 decades, carrying precision straight edges, calibrated squares, digital cameras, and computer-aided design software. What Christopher Dunn found across those 9 expeditions is physical evidence so specific, so measurable, and so impossible to explain with the tools Egyptologists claim were used that, after 50 years, mainstream archaeology has never once successfully refuted a single one of his measurements. They have ignored them. They have dismissed him as a fringe thinker without formal credentials. They have pointed out that he has appeared on television programs about ancient aliens, but they have never explained the marks. And the marks do not care about credentials. The marks are in the stone. To understand why Christopher Dunn's evidence matters, you need to understand the problem that has haunted Egyptology since an English surveyor first placed a measuring tool against the pyramids in 1883. The Great Pyramid of Giza contains approximately 2,300,000 blocks of stone. The vast majority are limestone, quarried locally from the Giza Plateau and stacked with methods that, while impressive, can be explained through known ancient engineering, ramps, sledges, levers, and an enormous labor force. Limestone is relatively soft. On the Mohs scale of mineral hardness, it rates between 3 and 4. You can scratch it with a steel nail. The real mystery is not the limestone. The real mystery is the granite. Granite is one of the hardest natural stones on Earth. Its primary component, quartz, rates 7 on the Mohs scale. For context, copper, the metal Egyptologists say was used to cut it, rates about 2.5. A hardened steel file, the kind a modern blacksmith uses, rates about 6.5. Granite is harder than all of them. Even with modern power tools fitted with diamond-tipped blades, cutting granite is slow, laborious, and eats through equipment. Yet the ancient Egyptians used granite everywhere. The king's chamber, the innermost sanctum of the Great Pyramid, is constructed entirely from enormous granite blocks, some weighing over 70 tons, transported from quarries at Aswan 500 miles to the south. The Valley Temple at Giza contains massive granite walls fitted together with joints so precise you cannot slide a razor blade between them. Obelisks weighing hundreds of tons were carved from single granite blocks and raised to the sky without a single crack. And on the surfaces of those granite blocks, from the pyramids in the north to the temples in the south, the ancient builders left marks. Saw marks, drill marks, polished surfaces so flat they reflect light like glass. Evidence of a manufacturing process that is, to put it plainly, impossible to replicate with the tools the official story says they had. The conventional explanation from mainstream Egyptology has remained essentially unchanged for over a century. Copper saws with sand as an abrasive for cutting, copper tubes with sand for drilling, dolerite pounders, heavy balls of very hard stone for shaping and smoothing. Patience, skill, and an unlimited supply of labor. There is just one problem: it does not work. Experimental archaeologists have tested copper tools with sand abrasive on granite. The results are consistent and consistently disappointing. Progress is measured in millimeters per hour. The copper wears away far faster than the granite because it is dramatically softer. The cuts produced are rough, uneven, and nothing like the smooth, precise marks found on ancient artifacts. One experienced stonemason, after examining ancient Egyptian granite work firsthand, said flatly that he had worked with granite using every technique available for 30 years and could not replicate what the ancients achieved. Not with ancient tools, not even with modern ones. Dolerite pounders do work for rough shaping, but they are agonizingly slow. Modern experiments suggest that shaping a single granite surface through percussion pounding requires hundreds of hours for even a small area. Scaling that up to the king's chamber or the 25 massive boxes of the serapeum at Saqqara would require millions of man-hours of labor for precision that pounding simply cannot achieve. Because here's the core issue. None of these techniques explains the precision. Not the speed, not the scale, but the precision. Surfaces flat to within thousandths of an inch. Drill holes perfectly circular and consistent in diameter from top to bottom. Saw cut straight and parallel over distances measured in feet. This level of accuracy requires measurement tools accurate enough to verify precision, cutting tools rigid enough to maintain alignment, and techniques consistent enough to reproduce results. This is not a new problem. Sir William Flinders Petrie recognized it 140 years ago. Petrie is not a fringe theorist. He is the father of modern Egyptology, the man who invented systematic archaeological excavation in Egypt, the man whose meticulous surveys of the Giza Plateau in 1883 remain among the most detailed ever conducted. His name is on the museum at University College London that houses some of the most important artifacts ever recovered from the ancient world. He is the gold standard. And Petrie, the gold standard, looked at the evidence on the granite and was disturbed. He documented saw marks on the north face of the sarcophagus inside the king's chamber and calculated the saws must have been at least 9 feet long. He found grooves in diorite, a stone even harder than granite, that were cut to a depth of 1/100th of an inch in what appeared to be a single pass. He examined basalt paving stones near the Great Pyramid and found parallel saw cuts with characteristics identical to industrial sawing. But it was the quarries that truly alarmed him. Scattered across the Giza Plateau were discarded cylindrical granite plugs, the remnants of a hole-making technique called trepanning, where a hollow tube is used to cut a circular groove and the central core is snapped out afterward. Petrie collected several of these cores. He studied them obsessively. He measured the grooves, and in his book, The Pyramids and Temples of Gizeh, he wrote a passage that should have changed Egyptology forever. He wrote that the grooves on these cores indicated cutting with fixed jewel points, not loose sand. He suggested the tools must have been set with corundum, sapphire, or diamond, because nothing softer could produce the marks he was seeing. He noted that the cutting rates were so extraordinary that he found himself revising his estimates upward multiple times within the same chapter. His own field quietly set those observations aside. They settled for the simpler story: copper and sand, patience and labor. And the problem sat there untouched for 100 years, until a machinist from Manchester picked up the exact same core that Petrie had puzzled over and recognized what he was holding. Christopher Dunn was born in Manchester, England, and began his career as an indentured apprentice in the traditional British system, years of intensive training under a master craftsman. His trade was precision manufacturing. He learned to read metal the way a musician reads sheet music, by feel, by instinct, by decades of repetition. He could tell you if a surface was off by 1,000th of an inch by running his fingernail across it. In 1969, an American aerospace company recruited him, and he emigrated to the United States. Over the next 5 decades, he worked at every level of high-technology manufacturing. Machinist, toolmaker, programmer, and operator of high-power industrial lasers. Project engineer, laser operations manager. He built parts for machines that needed to function at altitudes where a misaligned component means a plane falls out of the sky. These were his 5 decades of hands-on experience. His professional religion was simple. Precision does not occur by accident. Precision does not occur without purpose. And precision requires tools that are capable of producing it. When he first walked into the Great Pyramid in 1986 and touched the granite of the King's Chamber, he recognized something immediately. The flatness of those interior walls was not the work of a man with a hammer and a lot of patience. It was the work of a process, a controlled, repeatable, guided process that maintained tolerances across large surfaces. But the moment that truly defined his investigation came 13 years later in 1999 in a quiet room at the Petrie Museum in London. Dunn was given permission to personally handle and examine the drill cores Petrie had collected at Giza more than a century earlier. The drill cores themselves became central to his inquiry. He picked up core number 7, catalog number UC16306. It is a cylinder of granite roughly the size of a drinking glass with visible grooves spiraling around its surface. Petrie had described those grooves in 1883, but no one with Dunn's specific expertise had ever examined the core since. Core 7 would change that. What Dunn found confirmed Petrie's observations and added a critical detail. The groove was not a series of random scratches from sand rolling around in a hole. It was a single, continuous helix, like the thread on a machine bolt, traceable for 5 full rotations around the circumference of the core. It was uniform. It was consistent in depth and spacing. Here is the detail that demolishes the conventional explanation. The groove cut deeper through the quartz than through the softer feldspar surrounding it. This is the fact every viewer needs to understand, because it is the single piece of evidence that the copper and sand theory cannot survive. If you are grinding stone with loose sand tumbling randomly inside a copper tube, the sand does not discriminate between minerals. It wears everything at roughly the same rate. But on core number 7, the cutting agent bit deeper into the harder material. The only mechanism that produces this result is a fixed cutting point, embedded in or attached to the drill, being driven through the stone under controlled, sustained pressure. Loose sand cannot do this. A fixed abrasive, like a tooth on a saw blade, can. The feed rate, 1/10 of an inch per revolution through solid granite, is approximately 500 times faster than what modern diamond-tipped drills achieve at 900 revolutions per minute. Even accounting for the ancient drill spinning far more slowly than a modern motor, the cutting rate per revolution is extraordinary. It implies a tool that was not struggling against the granite. It was cutting through it with authority. Dunn said that when he held that core and traced the groove with his fingers, he knew he was looking at evidence of a machining process. Not a primitive one, a good one, a controlled one. The kind of process that leaves marks I recognize from my own shop floor. But core number 7 was just the appetizer. The main course was waiting underground 20 miles south of Giza in a place that had been sealed beneath the sand for 18 centuries. In 1850, the French archaeologist Auguste Mariette was in Egypt looking for Coptic manuscripts when he noticed something strange in the sand near the step pyramid of Djoser at Saqqara. A row of Sphinx statues, half buried, stretched in a line away from the known monuments. Classical writers, including the Roman geographer Strabo, had described an avenue of sphinxes leading to a buried temple complex called the serapeum. But the sarapium had been lost for over 18 centuries. No one knew where it was. Mariette followed the sphinxes. They led him to a sand-choked entrance cut into the bedrock. He organized a team to dig through, and what he found beneath the desert floor was one of the most extraordinary archaeological discoveries of the 19th century. A network of underground tunnels carved directly from the limestone bedrock, stretching hundreds of meters in total length. The main corridor was tall enough to walk through, dimly lit, with a vaulted ceiling carved from the living rock. Branching off the central walkway were individual crypts, each one recessed several feet below the tunnel floor behind massive stone doorways. And in the center of each crypt, resting in the darkness where it had sat for thousands of years, was an enormous stone box. 25 of them in total, each one carved from a single block of the hardest available stone. Rose granite from Aswan, over 500 miles away. Basalt, diorite, and even harder igneous rock from quarries at an even greater distance. Each box measured approximately 4 meters long, 2.3 meters wide, and 3.3 meters tall. Each weighed between 70 and 100 tons. The lids alone weighed 30 tons apiece, and every lid had been cut from the same block as its box. The official explanation was that these were sarcophagi for the sacred Apis bulls, living incarnations of a god that were mummified and entombed with elaborate ceremony. Bull skulls were found in niches in the tunnel walls. A statue of a bull was recovered and now sits in the Louvre. Christopher Dunn did not care what they were for. He cared about how they were made. Because anyone who has ever worked in precision manufacturing would walk into the serapeum, look at those boxes, and immediately recognize that something extraordinary happened here. In 1995, he entered the serapeum carrying a 6-inch precision straight edge, accurate to 2/10,000ths of an inch. He placed it against the inside walls of the first box he could access. He shone a flashlight behind the straight edge. No light. Zero. The surface was so perfectly flat that his precision instrument, the kind used to calibrate machinery in aerospace factories, could not detect a gap. He slid the straight edge along the wall. Still no light. He moved to the floor of the box. No light. He checked the other wall. No light. He returned in 2001 with an even more precise tool, a calibrated precision square accurate to 5/100,000ths of an inch, verified on a Jones and Lamson comparator. He climbed inside one of the boxes, a man standing inside a granite container the size of a small room, and pressed his square into the corner where the 30-ton lid met the interior wall. Square. Not approximately, not impressively close. Square to a tolerance of 5/100,000ths of an inch, 1/20th the width of a human hair. He checked the opposite side. Square there too. The geometric implication of this is what makes it devastating. For the lid to be square with both interior walls, those walls must be parallel to each other across the entire vertical span of the box. The top surface must form a plane that is perpendicular to both sides simultaneously, and the flatness of each individual surface must be maintained across areas measuring 5 feet and 10 feet apart. This is not craftsmanship in the way we romanticize it. This is manufacturing. This is the kind of work you see in a temperature-controlled metrology lab where parts for particle accelerators are inspected. And it was done in granite underground, supposedly with copper tools. Dunn measured the inside corner radii. In modern machining, when you mill out a cavity, the rotating cutting tool leaves a small radius in each corner because the tool itself is round. The size of that radius tells you the size of the tool. The corners inside the serapium boxes had radii of just 4 millimeters. A pencil could nestle into them. He then asked a modern American stone fabrication company if they could produce a replica of one serapium box from a single block of granite. Their answer was blunt. Even with unlimited money, unlimited time, and every piece of equipment in their facility, they would need to assemble it from 6 separate pieces. They could not carve one from a single block. The ancients produced 25. Now here is the moment that requires no engineering degree, no understanding of the Mohs scale, and no knowledge of metrology to appreciate. This is the piece of evidence that you are going to want to share. Christopher Dunn traveled to the Luxor Temple in southern Egypt, where 2 colossal statues of Ramses II sit at the entrance, carved from single blocks of red Aswan granite. Over 100 statues of Ramses exist across Egypt, from Memphis to Abu Simbel in various sizes, but always in the same distinctive style. Dunn mounted his camera on a tripod to eliminate even the slightest hand tremor. He photographed the face of Ramses straight on. Then he took the images home and loaded them into the same computer-aided design software used to design aircraft wings and turbine blades. He split the image down the center line of the face. He mirrored one half and overlaid it on the other. They matched. The left side of the face of Ramses II is a precise mirror image of the right side. Not almost. Not impressively close, mathematically precise. The eyes line up, the nostrils line up, the curve of the lips line up, the rise of the cheekbones lines up. Every contour, every feature, every curve. He then analyzed the proportions. The distances between features follow Pythagorean triangles. The curves of the face trace Fibonacci spirals. The framing of the features fits inside golden rectangles. And this identical geometric template appears across every Ramses statue he measured. At Luxor, at Memphis, at the Ramesseum. Different locations, different sizes, same mathematical DNA. Think about what that means. Over 100 statues at sites hundreds of miles apart, carved from the hardest stone available, each face a mirror image of itself, each face obeying the same geometric rules. This is not the work of 100 different sculptors, each interpreting a royal face by eye. This is standardized reproduction. This is what happens when you have a template and a machine-guided process that follows it. Any sculptor will tell you that perfect bilateral symmetry in a hand-carved three-dimensional curved surface is essentially impossible. The human hand wobbles, the chisel bites unevenly, micro-variations accumulate with every stroke. That is why no hand-carved statue in the Greek, Roman, or Renaissance traditions achieves the kind of symmetry that a computer finds in every Ramses head. Dunn said simply, "That is not a whimsical stroke of a chisel." While Dunn was gathering his evidence in Egypt, confirmation was emerging from a source that the academic establishment could not dismiss. In 2015, Anna Serotta, an associate conservator, and Federico Caro, a research scientist, both working at the Metropolitan Museum of Art in New York, published a discovery that would have made Flinders Petrie weep. They examined a small, visually unremarkable fragment of limestone, catalog number 57.180.142, excavated from the Great Aten Temple at Amarna in 1891. The fragment had tiny drill holes in its surface. Using scanning electron microscopy and energy dispersive X-ray spectroscopy, the same analytical techniques Dunn had long argued should be applied to ancient artifacts, they examined what was embedded in those drill holes. They found corundum, aluminum oxide, with a Mohs hardness of 9, the second hardest natural mineral on Earth after diamond. The same substance used in modern industrial grinding wheels and precision cutting tools. The same mineral that forms rubies and sapphires. The material that lines the inside of every high-grade piece of sandpaper you have ever used. And it was sitting inside a drill hole made over 3,300 years ago. The corundum was not alone. It was mixed with quartz, rutile, and feldspar in a granular compound that showed clear signs of deliberate preparation. The particle sizes were consistent. The mixture was not random geological debris. This was not contamination from later centuries. This was an engineered abrasive compound, prepared by someone who understood mineral hardness, applied to a bronze tubular drill, and used to bore through stone with an efficiency that quartz sand alone could never achieve. The researchers noted something else that deepened the mystery. The mineral assemblage they found did not match the composition of emery from the island of Naxos in Greece, which had been the most commonly discussed ancient source of corundum abrasive in the Mediterranean world. The Amarna material was different, suggesting either a different geological source, a deliberate manufacturing process that selected and refined specific minerals, or possibly the recycling and regrinding of abrasive material across multiple uses. There is a known corundum deposit at Hafafet in Egypt's eastern desert, but the connection remains unconfirmed. What has been confirmed is this. The ancient Egyptians were using corundum-bearing abrasives. They were preparing them in specific mixtures with controlled particle sizes. They were applying them with metal drilling tools to cut through stone. And they were doing this at a minimum 3,300 years ago, and likely much earlier, given that the techniques visible in Old Kingdom monuments from the Pyramid Age are even more impressive than those found at Amarna. For 140 years, mainstream Egyptology had insisted, sometimes aggressively, that the ancient Egyptians used only quartz sand as an abrasive. Quartz rate 7 on the Mohs scale, adequate for limestone, but marginal for granite. Multiple researchers who suggested corundum or emery use were challenged, dismissed, or simply ignored because no physical evidence had been found in Egypt itself. The absence of evidence was treated as evidence of absence. Then Anna Serotta and Federico Caro found the evidence in a drill hole, in a fragment that had been sitting in a museum drawer for over a century. The discovery proved that the conventional story about sand as the sole abrasive was incomplete. The ancient Egyptians had access to abrasive technology dramatically more powerful than what the textbooks described, and someone had to source the material, transport it, prepare it to the right particle specifications, and understand its properties well enough to deploy it effectively in combination with metal tools. This is not primitive trial and error. This is applied material science. This is exactly what Petrie suspected in 1883 and what Christopher Dunn has been arguing since 1998. What does all of this add up to? Let us lay the evidence out piece by piece and see what picture emerges. Christopher Dunn has never claimed that ancient Egyptians had lasers or power tools in the modern sense. He has never claimed alien intervention, despite being associated with television programs that discuss such ideas. What he has consistently argued, backed by decades of measurable physical evidence, is that the ancient Egyptians possessed a level of manufacturing capability, material science knowledge, and engineering sophistication that mainstream Egyptology has systematically underestimated. Not by a small margin, by a fundamental misunderstanding of what the evidence actually shows. Consider the evidence chain. Flinders Petrie, the founder of scientific Egyptology, measured drill cores at Giza in 1883 and found feed rates he called astonishing, cutting speeds through granite that exceeded anything he could explain with conventional tools. He proposed corundum or diamond-tipped implements. His own discipline quietly set this aside and never revisited it. 116 years later, Christopher Dunn, a manufacturing engineer with 50 years of precision machining experience, examined the same core at the Petrie Museum and confirmed everything Petrie had found. He identified the groove as a single continuous helix, not random scoring, and noted that it cut deeper through the harder mineral in the granite, a characteristic only possible with a fixed cutting point under controlled pressure. No experiment using copper tubes and loose sand has ever replicated this. At the serapeum of Saqqara, Dunn measured 25 granite boxes weighing up to 100 tons each and found interior surfaces flat to within 2 ten-thousandths of an inch, corners square to 5 100,000ths of an inch, and corner radii of just 4 millimeters. A modern American fabrication company told him they could not reproduce even one such box from a single granite block with current equipment. The ancients made 25 and installed them underground in tunnels barely wider than the boxes themselves. The level of precision is extraordinary. At Luxor, Memphis, and the Ramesseum, Dunn's computer analysis of the statues of Ramses II revealed perfect bilateral symmetry and consistent geometric relationships. Pythagorean triangles, Fibonacci spirals, golden rectangles reproduced identically across more than 100 statues carved from some of the hardest stone on the planet. No sculptor in any era has achieved this level of mathematical consistency by hand. And in 2015, the Metropolitan Museum of Art published peer-reviewed evidence that corundum, a mineral with a hardness of 9 on the Mohs scale, was found embedded in an ancient Egyptian drill hole, confirming that the Egyptians had access to industrial-grade abrasive technology that mainstream Egyptology had denied for over a century. Corundum in an ancient drill hole changes the discussion. Each piece of evidence, taken alone, might be explained away, but taken together, they form a pattern that demands a response. The drill cores, the serapeum precision, the Ramses symmetry, and the corundum all point in the same direction. The ancient Egyptians knew more about working stone than we have given them credit for. Far more. Dunn is not asking anyone to believe in lost civilizations or ancient power plants. He is asking them to look at the marks, to measure what he has measured, to verify what he has verified, and to come up with a better explanation than copper, sand, and patience. Because after 50 years of asking, no one has. Not one Egyptologist has published a peer-reviewed replication of the serapeum precision using the tools they claim were used. Not one experimental archaeologist has produced a drill core with the feed rate and helical characteristics of core number 7 using copper and sand. Not one computer analysis has demonstrated how bilateral symmetry this precise can be achieved in granite by hand carving. The silence is the loudest evidence of all. He has said, and I think this captures everything. I am a bell ringer. I am saying you guys need to look at this a little closer and do your homework. The straight edge does not lie. The precision square does not lie. The spiral groove on core number 7 does not lie. The corundum in a drill hole from the reign of Akhenaten does not lie. And the perfect mirror symmetry of a pharaoh's face carved in granite, reproduced 100 times across 1,000 miles of desert, does not lie. These are not theories. These are not interpretations. These are not speculation. They are measurements. Physical, verifiable, repeatable measurements taken with calibrated instruments by a man who has spent his life building parts where 1,000th of an inch matters. And measurements do not care about credentials. They do not care whether you have a PhD or a factory badge. They do not care whether the academic establishment is comfortable with what they reveal. They simply are what they are. The greatest library the ancient Egyptians ever built is not a collection of papyrus scrolls. It is not a wall of hieroglyphs in a pharaoh's tomb. It is the marks they left in the stone itself. Cut marks, drill marks, polished surfaces, spiral grooves, geometric relationships, and abrasive residues encoded in granite so hard it has survived 4.5 millennia without a scratch. Those marks are the message, written not in words but in precision, not in language but in tolerances. And Christopher Dunn, a machinist from Manchester, England, who spent his life learning to read the language of manufacturing, may be the first person in the modern world trained to understand what the ancient builders were actually saying. The stones of Egypt have been speaking for 45 centuries. We just were not listening. Now we are. If this story fascinated you, subscribe to the channel. The evidence is still being uncovered. And if Christopher Dunn is right about the marks in the granite, we need to ask a much bigger question. What else have we been wrong about?